humble Christmas pudding. Perhaps the single most divisive conglomeration of Christmas currants. Granny loves it though, so you've got to have one every year. But thanks to SolidWorks Flow Simulation, we can remove at least one Christmas Day argument and work out just how long we need to leave our pudding to cool, so poor Granny doesn't melt her dentures. In true Blue Peter style, here's one I made earlier. 400 grams of lovely Christmas pudding, made from a simple revolve and topped with a delicious fillet. We've thrown on a custom appearance to give it that traditional brown colouring and served it on a festive plate. Reverse engineering the pudding, I've calculated the density and the specific heat capacity of the mixture which, along with the thermal conductivity, are vital properties that we need to know to simulate the heating and cooling of any object within SolidWorks. Before we can cool anything though, we first need to heat it up. It's time to steam our pudding in the oven at 160 degrees for an hour. I've simplified our conventional oven into a box of equal volume and position the pudding inside at the level of the middle shelf. With the SolidWorks Flow Simulation Wizard, I've set up a new study in Celsius to look at heat conduction in solids with a time dependency, running the study for an hour or 3,600 seconds. We'll also account for the presence of that little known force, gravity. Air is our default gas within the model, and we'll assume that our default solid is our Christmas pudding. To simulate the conditions inside an oven, I've set the wall temperature to 160 degrees Celsius, and also set the default fluid and solid temperatures to 160 degrees Celsius. I've defined the solid material of the pudding with the one I created earlier, and set the initial conditions of the pudding to be room temperature at 21 degrees Celsius. We're interested in the average and maximum temperature that the solid body reaches, so I've set up two goals to monitor them during the simulation. We'll also enable the Transient Explorer options to look back at how the temperature changes over time. Now it's heating up pretty nicely, and we've got our maximum average temperature of 157 degrees Celsius. We can take a look at some cut plots and see how the temperature changes throughout the model. Granny's getting impatient for her pudding now, and the kids want to finish unwrapping their presents, so let's find out how long you need to leave this pudding to cool to minimise the pre-pudding entertainment time. Let's get our steam pudding out and pop it on this festive plate on this remarkably clean kitchen counter. Again, we need to use a simplified model, so here's a rather bland kitchen severely lacking in any privacy. This time we're setting up the study through the wizard with our default fluid as room temperature air, although this is a kitchen just after cooking Christmas dinner, so we can bump it up a few degrees. We'll put it about 25 degrees Celsius and also define our default solid as lightweight plywood to account for the kitchen cabinets. We need to make sure heat conduction in solids, time dependency and gravity are selected and assign our pudding and porcelain materials. We can then set our initial conditions for the pudding part to be 157 degrees Celsius, the hottest average temperature we simulated during heating. It's time to assign some goals. Again, we're looking at maximum and average temperatures of the solid before we need to refine our mesh a little bit by adding in a local mesh around the pudding area. This just gives us a little bit more control and allows us to see more accurate results. Under calculation controls, we'll set the study to finish once the selected goals have converged, the goal being when the average temperature of the pudding reaches 40 degrees Celsius, around an edible temperature. Again, we'll make sure the Transient Explorer is set to save periodically and run the study. We can take a look at some surface plots and see how our temperature changes over time. So there we have it, we've steamed our pudding and found that we should leave it about 22 minutes before we start tucking in. Of course, this timing is very much dependent on how hot your kitchen is, any airflow through it, and whether any pesky children have stolen chunks of it before you've even had a chance to sit down. Make sure to try this at home with your Christmas pudding and prove to your own family how long your puddings, or any of that delicious feast, should be left alone for. We wish you a very Merry Christmas and a Happy New Year from all of us at Solid Solutions.